Good morning, Adam Eldridge, teacher at West Valley High School in Yakima, here giving you a lecture on Central Washington University's Section 7.1 in Pre-Cal. So what are we going to learn about today? We're going to talk about radian measure, converting between radians and degrees, finding exact values of trig functions for angles given a radian measure. So to start with today, let's go ahead and look at the definition of radian measure. It says if we place the vertex of an angle at the center of a circle, so let me grab my pen here, and if we start by drawing a circle, label that center, draw in our radius, r, and let's let s denote the length of the arc. So when we're talking about the length of the arc, we're talking just about this portion right here. Then the radian measure of angle theta, which is located right here. Angle measure of angle theta is the ratio of the arc length s to the radius r. So we know that theta in radians is defined as the arc length divided by the radius. So theta is equal to s over r. Now another way of looking at the definition of a radian is to say that a central angle of a circle has a measure of 1 radian if it intercepts an arc with the same length as the radius. So if my radius is the same as my s, then my angle has a measure of 1 radian. Some of the advantages of radians versus degrees is that radians can take on whatever units we need them to. Again, since we're taking a ratio of the arc length compared to the radius, whatever units those arc length and radius are in will cancel out. Versus degrees, which is 1 degree is equal to 1/360th of a full revolution. Here with radians, we can take whatever units we need and apply them to the situation. As we'll look at in section 7.3, it allows us to take a real number input rather than a degree input when we start looking at inputting things into trig functions. So let's look at an example of calculating the radian measure of an angle. So in this circle with radius of 4, we have an intercepted arc of 10 centimeters. Take a moment and calculate that angle in radian measure. We know that theta is equal to s over r, which our arc length in this case is 10 centimeters, and our radius is 4 centimeters, which yields a central angle of 5/2 radians. Now, one of our other objectives today is to be able to convert between radians and degree measures. So we're going to start here with a central angle that is 90 degrees. So we're starting with a right angle. And we will call the radius of this circle r. Now from our earlier discussion, it's a 90-degree angle. From our earlier discussion, we know that the angle, the central angle in radians, is equal to the arc length divided by the radius. Now taking us back to geometry, we know that arc length is a portion of the circumference. So to redefine s in terms of r, the arc length, s in this particular problem, is 1/4 the circumference of our entire circle. Now where I got the 1/4 is, that's 90 degrees for our angle divided by 360. So that's where I got that 1/4 from. So from geometry, we remember that the circumference of a circle is either pi times diameter or 2 pi r. We're going to go ahead and do it in terms of the radius. So we know that for this particular problem, the arc length for this arc is pi over 2 times the radius. Substituting that value for s back in, we can see for this particular problem that we have pi over 2 times r divided by r, which yields pi over 2. Pi over 2 represents the radian measure of that angle, but we know that we started with this angle being equal to 90 degrees. So from this, we can develop the common conversion factor for radians to degrees, and that's to say that pi radians is equivalent to 180 degrees. So when we talk about conversion factors, let's remind you of some from your previous math lives. You know that 1 foot, for instance, is the same as 12 inches. So much in the same way that we would convert between feet and inches, we're going to do similar conversions between radians and degrees. So let's look at an example here. Let's say that I want to take 3 pi over 2 radians, and I wanted to convert that into degrees. Well, I know my units are currently radians, so I want to multiply by the conversion factor that has radians in my denominator. So pi radians, and I'm going to put my 180 degrees on top. The radians will essentially cancel here, and we are left with, and the pi's will also cancel. 2 cancels into 180 to yield 90, and we are left with 270 degrees. Now, if I wanted to go from degrees to radians, like if we started with 60 degrees, we're going to use the same conversion factor. We are just going to put the degrees in the denominator and pi radians in the numerator. And this becomes pi over 3 radians. So now let's try a couple on your own. Please convert 17 degrees to radian measure and convert 4 radians to degree measure. So if I start with 17 degrees, times pi over 180. That yields 17 pi over 180, which in a moment we can go and do an approximation of that on the calculator. That is a radian measure. For the 4 radians, times 180 degrees over pi radians. 4 times 180 is 720 degrees over pi. And a lot of my students will forget about the pi down there. Oftentimes, we'll have a pi located over here in our original radian measure, and those will cancel. But in this particular case, the pi's don't cancel. So we have 720 degrees divided by pi. Remember, pi is just a number. It's approximately 3.14. So now if we head over to the calculator, we can look at taking 17 times pi and dividing that by 180, which is approximately 0.30. And if we take the 4 radians times our 180 divided by pi, we had approximately 229.2 degrees. So there was an example of converting from degrees to radians and from radians 2 degrees. So let's go back to the unit circle. And you discussed this a little bit back in chapter 6. Except for today, we're going to look at it in terms of radians instead of degrees. So we're going to talk about an angle in standard position. Right here would be 0 radians, much like it's 0 degrees. In degrees, we talked about one full revolution being 360 degrees. Well, today we're looking at, instead of 360 degrees, we're going to say that one complete revolution is 2 pi. So I start with my full circle, and if I cut that circle in half, the angle that would be from here to here would be pi radians. 1 pi, and then coming all the way back around puts us at 2 pi. Now if I cut each of those in half, so if I take my angle that represented pi, and I cut that in half, I'm now looking at a pi over 2. So I've taken the whole circle and cut it into 4 pieces, each one of which has a measure of pi over 2 radians. So right here would be 1 pi over 2, 2 pi over 2. Down here we're at 3 pi over 2. And 4 pi over 2, which is equivalent to 2 pi. If we then cut each of those sections in half, we'll have the whole circle cut up into 8 pieces. So if I take a pi over 2 and I divide it in half, I end up with a pi over 4. So here is pi over 4, 2 pi over 4, which is equivalent to pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4 puts us back at 2 pi. Now in terms of degree equivalence, we know that a pi over 2 is 90, and a pi over 4 is 45 degrees. Which, if we think back to the usefulness of our special right triangles, a 45-degree angle is pretty common when we talk about an isosceles right triangle and the special relationships that exist. So we'll be coming back to the fact that pi over 4 is equivalent to 45 degrees later on. I've got another circle here that I want to start with. Again, this is 0, and we have pi over here. Now instead of cutting this into halves again, let's say that I cut the whole circle into 6 pieces. So if I were to take my marks here, cut it into 6 equal pieces, I'm taking that 2 pi and cutting it into 6 pieces. That means that each of those pieces is a pi over 3. So here's 1 pi over 3, there's 2 pi over 3, 3 pi over 3 is pi, 4 pi over 3, 5 pi over 3, and 6 pi over 3, which is equivalent to 2 pi. Now, pi over 3, again, if we're taking the whole circle and cutting it into 6 equal pieces, that means that our 60 degrees is equivalent to pi over 3 radians. Now, if I take each of those and cut those in half, again, we're taking a pi over 3 and cutting it into half. That's a pi over 6. So we have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. Over here we have 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, and 11 pi over 6. Again, these are the common ones we're going to see because on the triangle here on the right, we're dealing with multiples of pi over 6, or 30 degrees, which puts us on the special right triangle, 30, 60, 90, or in the case of radians, pi over 6, pi over 3, pi over 2. So let's take a moment and evaluate approximate values of trig functions for angles in radians. So you'll notice here that I've asked you to find the cosine of 3. That's not 3 degrees, it's 3 radians. If we don't see the little degree mark, then we are in radians. And then I've also looked for tangent of 4 pi over 2. And before we do that, I want to draw a quick picture to remind us where is 3 radians. If we're starting here and we're working in the counterclockwise direction, well, we know that right here is pi, which is approximately 3.14, so we should see an answer here that is going to be in the ballpark of about -1 from our earlier discussions about cosine values. Because right here, the cosine of pi is going to be -1, so I'm expecting a value that's somewhat close to -1. If I'm looking at the tangent of 4.2, well, here is 3.14. Down here would be approximately this would be 3 pi over 2, which I don't want to throw an approximation out there. It's between 4 and 5, so I'm looking at an angle that's somewhere right in here. And we know that tangent from our earlier discussions is positive in that third quadrant. So cosine, I'm looking for a negative value, and tangent, I'm looking for a positive value. So let's go over to the calculator. And here's where it's important to know what mode our calculator is in. So before computing these values, I'm going to go ahead and hit our mode. And we are in degree mode currently. And I'm wanting us to get into radian mode. So I'm going to arrow down to the radian and hit enter. And so now I'm in radian mode. Get back to my home screen and compute the value of the sine, we're going to do cosine of 3. And we find that that value is approximately -1, which is something we had assumed from our earlier picture. And calculating tangent of 4.2, we get a value of about 1.8, which again is positive, as tangent should be in the third quadrant. Finally, let's look at evaluating some exact values of trig functions. So I've got a couple examples that I want to work through here quickly. The first one is, let's compute the sine of 4 pi over 3. So when looking for exact values, I always like to draw a picture here to help me evaluate trig functions. So from our earlier unit circle discussion, we know that 4 pi over 3 is going to be located down here in quadrant 3. So here is 4 pi over 3. Now that's going to behave similarly to the value of sine of pi over 3. That little angle right in here between the x-axis and the terminal side of my angle is a pi over 3. I know something about pi over 3. I know that pi over 3 is 60 degrees. It's the equivalent of 60 degrees. And I know that if I were to construct a right triangle here by drawing a line from the end of my terminal ray back to the x-axis, I can create a 30, 60, 90 triangle where this angle is 60 degrees. And I know the ratio of sides in a 30, 60, 90 triangle are 1, square root of 3, and 2. And here's a notation I haven't seen in very many textbooks, but it's something I like to share with my students. When I look at this picture, I'm going to put a negative in front of my 1 here because this has a negative x value. And I'm also going to put a negative in front of the root 3 value because I'm below the y-axis. So because I'm to the left of the x-axis, I'm drawing in my side of my triangle with a -1, and because I'm below the y-axis, I'm putting my y as a negative as well. I always leave my radius positive, and I'm not bound by the unit circle. If I were to draw the circle here, I would actually be looking at a radius of 2. But let's remember that trig functions, the output is a ratio of sides. So it doesn't matter how big our radius is, the ratios are going to be the same. I know from earlier discussions, our SOHCAHTOA, that sine is equal to the opposite over the hypotenuse. So I can come over here and look at negative root 3 over 2. Now, you may have looked at this in a different way. You previously may have said, okay, I know that the sine of pi over 3 is equal to root 3 over 2. And then because the sine goes with the y value, we know that the y in quadrant 3 is negative, so sine of 4 pi over 3 must be negative as well. So there's a couple approaches depending upon how your textbook looks at this particular problem. Let's look at one more example here. Let's look at the tangent of negative 3 pi over 4. And again, I like to draw a picture to help me out here. If I'm looking at an angle of negative 3 pi over 4, I'm starting, and because of the negative, I'm going in the clockwise direction. And I know that the value here would be negative pi, so I'm pi over 4 units away from negative pi when I'm at negative 3 pi over 4. I can draw a little reference triangle here. I know that a pi over 4 corresponds to a 45-degree angle, so I know that this is an isosceles right triangle I've created. So ratios of sides is 1 to 1 to root 2. And again, because I'm hanging out down in quadrant 3, I like to put a negative on my x and my y, just to remind me that the x values are negative in quadrant 3 and the y values are negative in quadrant 3. The tangent of this angle is equal to the opposite over the adjacent. So value is negative 1 over negative 1, which is 1. And you can take a moment and verify those on your calculator as well. And that concludes our discussion of basics of radian measure and calculating exact values of trig functions in radian measure.